So let's try to determine the current required in the wire to help the loop float. The loop has got a mass m and a resistance per unit length lambda. So the first step in understanding this problem is to determine why the loop should float at all in the first place. So to this end, let's try to plot some magnetic field lines. By the Biot-Savart grasping rule, if you put your thumb in the direction of the current, the fingers will give you the direction of the magnetic field, the right hand rule. So in this case, the magnetic field is going to be large, close to the wire, because the magnetic field of a long wire decreases as 1 over r, and then the magnetic field is progressively going to get smaller away from the wire, so which I'll indicate here by making these dots less thick. So that's the magnetic field profile. Now what we require is for the loop to somehow stay afloat. Now how is that even possible? That's managed by changing this current. So let's try to understand how this current should even change. Should it increase or decrease? For the loop to float, the force on the lower part of this loop should be bigger than the force on the upper part. So the current induced, remember that like currents attract, unlike currents repel. So we want unlike current in the lower part of the loop. In other words, we want a current that goes in this direction. Okay. So first of all, that determines the direction of the induced current in the lower part of the loop, and hence also the upper part of the loop. The sides are unimportant because they're going to cancel out. Now, when you have this lower part of the loop where the current is going to be in the opposite direction, now opposite currents repel. So this force is going to be much bigger. I'm going to draw this much bigger force with an arrow like this, and that attraction force is going to be much smaller because it's much farther away from the wire below. So that attraction force I'll write like that. I'll call this F sub u, and I'll call that F sub d for down. So this all looks good. It looks like the loop is in fact going to levitate. Now what makes this kind of current happen? A current like this, let's find out the direction in which the magnetic field is produced by a current like this. A current like this will produce a magnetic field into the page. You can do this either by using the right hand finger rule or by using the Biot-Savart rule again. So a magnetic field into the page is created by a clockwise induced current, which means that this magnetic field is created in response to this magnetic field by the wire being bigger. Why else would the loop fight back in that manner? So from just understanding why the loop is levitating, we already know that I of t, the current that must be sent in the wire below, must increase with time. Because if it does not increase with time, let's run over the argument again. Let's suppose it does not increase with time. Then there'll be no reason for this induced current to be there at all. If it decreases with time, let's try the opposite. If it decreases with time, then these magnetic field lines coming out of the page will actually be smaller. And so this loop will be motivated to create more field outside the page, and that would require a current in the other direction, in this direction. But that current would make these two like currents, and like currents attract. So this loop is never going to float. It's going to collapse right into the wire. So the only conclusion we have is I of t must increase with time. All right, so this is all looking very good. All we need now to do is to find an expression of I of t and all these forces, and then figure out how the balance happens. So let's proceed to do this problem. It's just a Faraday law problem at this point. You just have to carry through the steps. So let's find first the induced EMF. The induced EMF E prime is negative rate of change of the magnetic flux. I'll call it the open magnetic flux because the flux through the open surface, that is the area of the rectangle. The flux itself is defined as the double integral of B dot dA. Now this double integral, it looks scary, but it's really not, because here the area we're talking about is the area of a rectangle. And observe that when we calculate this area element, all we really need is the length times the entire length times this width, which is dy. Let's take the strip to be some distance y away from the wire. The magnetic field of an infinite wire is B of y equals mu naught I of t, that's the current here, divided by 2 pi y being the distance from the wire. So we have all the expressions that we need. Now the dA vector, how is it calculated in relation to the B vector? In other words, what is the dot product? For that one, we have to talk about the direction of the area vector. The area vector direction comes directly from the direction of the induced current. If the induced current is clockwise, the area vector is into the page. So the angle between the B field and the area vector is 180 degrees. So that gives me the integral from y equals r to r plus w, because that's the lower and the upper limits of the loop, the magnetic field as a function of y times the area element of the strip, which is L dy, cosine of 180 degrees. So now we have all our ducks in a row. We just have to integrate. That's not too hard to do. Let's put the negative sign outside, and L also comes outside along with mu naught and 2 pi. So mu naught L over 2 pi. And then I just have, actually the I also is a constant, because although it does depend on time, it does not depend on y. Then I just have dy divided by y from r to r plus w. And that's your natural log there. So that's minus mu naught Li over 2 pi, natural log of r plus w divided by r, which is just a number. The loop is levitating, it's not moving here and there, so this all is fixed. So the only thing that varies with time is I here. I'll stop writing I as a function of time. It's understood that I is a function of time, just to save space in writing. The EMF by Faraday's law is a negative derivative with respect to time of the flux. Well, the flux is that, so let's figure out the EMF next. The EMF, E prime, I like to put primes for all the induced quantities. Because of the minus sign there, this minus sign disappears, and that gives me mu naught L over 2 prime times di by dt, natural log of r plus w over r. Okay, the induced current next is the induced EMF divided by the resistance of the loop, and the resistance of the loop is none other than the resistance per unit length times the total length of the loop. The total length of the loop is the circumference, which is 2L plus 2W, so that's 2 times L plus W. Okay, now the last step is to find the forces. The force is got by the Lorentz force formula, which is given by F equals the magnetic force F sub E is I prime L cross B. Let's actually find out the directions of the magnetic force. On this one, the direction of L is the same as the direction of I prime if it's a conventional current. So I prime L is this way, cross B. Yep, it is up as we deduced it should be. And on this one, it's going to be down. So let's find the expressions. The angle between L and B is 90 degrees. So F sub up is going to be I prime capital L B at the location R sine 90 degrees. These are just magnitudes I'm writing. F sub d is I prime L B at the location R plus W sine 90 degrees. And the net force, which is F sub u minus F sub d, should be equal to the mass of the loop. So we have this second law equation for the equilibrium. Sum of all the forces in the y direction equals 0. Tells me that mg must be equal to F sub u minus F sub d. Net force down equals net force up is what I'm really doing here. So that's I prime L B of R minus B of R plus W. So B of R is that function there. So that's mu naught times I divided by 2 pi 1 over R minus 1 over R plus W. Observe this quantity on the right side is positive because R is smaller than R plus W, and 1 over the small quantity is bigger than 1 over the large quantity. So let's take the common denominator here to make it look nicer. So that gives me I prime times I mu naught L over 2 pi. The numerator becomes R plus W minus R, which is just W, and the denominator is R times R plus W. Great. So this gives us an equation for I prime I. I prime I, where I prime is the induced current, remember, and I is the regular current. Let me write I prime I first. It's going to be mg 2 pi mg R times R plus W divided by mu naught LW. Okay, not too bad. Now what is I prime? I prime is E prime over 2 lambda L plus W. So that times I is equal to 2 pi mg R times R plus W over mu naught LW. So it's looking a little bit crazy already, but that's not our concern. Our concern is not how complicated things look, but if we can do the problem or not. E prime is all of this. So let's now put that in. So I get E prime, which is mu naught L over 2 pi di by dt natural log of R plus W over R divided, that's E prime alone, divided by 2 lambda L plus W times I is equal to 2 pi mg R plus W over mu naught LW. So you look at that thing, it looks pretty impressive at this point. Now I'm going to solve for I times di by dt on the left side and move everything else to the right side. So let's see if I can do this without any mistakes. So I'm going to move 2 on the other side. So there's 4 lambda up here, lambda L plus W also up there. 4 lambda, I'll put the pi here, pi L plus W times mgr R plus W over mu naught, and then there's a mu naught from down there. Oh, there's a 2 pi here which goes up here and makes this 8 pi squared. So mu naught times mu naught squared, because that comes down here, L squared, because that also comes down here, natural log R plus W over R. I think I've done this right. If not, you can email me. But the upshot is all this is a constant. I'm going to call this constant A. And now I don't have to think about that constant anymore. This is a very interesting equation. It's a differential equation, but you know, this is just 1/2 of d by dt of I squared. Is it not? Because d by dt I squared is 2i di by dt. And that 2 cancels with 1/2. And that's equal to A, which tells me that I squared equals 2a di squared equals 2a dt. Now let's integrate both sides. If I integrate both sides, I'm going to get I squared is equal to a times 2a times t plus a constant. Well, at time t equals 0, I can take my current to be 0, so the constant can be taken to be 0. Okay, so at time t equal to 0, the current is, well, let's say it's I naught. I don't want to make it 0. So at t equals 0, let's say the current I equals I naught. That'll, I naught, yeah. So when t equals 0, if I equals I naught, then that's going to be I naught squared. So C is I naught squared. So I'm going to get the current I is equal to 2AT. Well, let me take that to be 0. I don't really care. The square root. And that's the function where A is this monster that satisfies this problem. So I've solved this problem.